Take it away,
In this
Steve.
presentation,
Okay, here goes.
I'm going to talk about the rationale and logistics of my project known as VanderBot, which uses Python scripts to make humans more efficient editors of Wikidata. I'll talk a little bit of an overview about bots, and then some details about Wikidata, its infrastructure, the model behind it, and the identifiers it uses. And I will end by talking about the structure of the CSV files that I use to hold the data that will be written to Wikidata, and then a little bit about how VanderBot itself works. Most people have heard of bots, so I want to take just a moment to talk about what that means. I don't know the exact definition of a bot, but in the context of Wikidata, a bot is essentially software that can read and write to the Wikidata API. They can be autonomous, in other words, working without human intervention, and autonomous bots typically have one particular task they use, or they can be non-autonomous, in which a human monitors what they're doing and might intervene. It's this second category that I'm the most interested in. The pros and cons of humans versus bots are that humans do work that's much higher quality, but also much lower speed. One of our star editors, Greg Weldy at Vanderbilt, can do about 160 edits per day of high quality. Compare that to a Wikidata bot, which can make 3,000 edits per hour. But the quality of those edits is often much worse than the quality of a human. Just to give you an example, here is an item about the researcher S. Mishra. As you can see, there are no references. There is an ORCID ID, but there's very little information provided. We can see that this record was created by a bot called Large Database Bot. And one of the reasons why I call this a dumb bot is that with the ORCID ID, we could actually go to the ORCID website and find out what S. Mishra's given name was, and that it was Sanju, but this bot didn't bother to do that. So by a dumb bot, I'm essentially talking about ones that don't make use of available linked information. Oftentimes they're writing authoritative data that they have available to them, but without considering existing data in Wikidata. And also many times these kinds of bots do not bother to write references. The kind of bot that I'm interested in, and the kind of bot that VanderBot is, will look up things for humans via APIs and Sparkle queries, and then can disambiguate existing data and avoid duplicating it, only calling in the humans for assistance when necessary. And also it can add references if they're missing. So with the assistance of a bot like this, I can edit about 200 items per hour, and this is not 200 statements because each one of the items might have multiple statements. So compared to editing 40 statements per hour, which would be a typical rate for a human, this is way, way faster with the assistance of the computer. If we wanted to sort of visualize this schematically, this is what a dumb bot does. It has some kind of data source. That source gets run through a script, which then writes the data to Wikidata through the MediaWiki API. If you're a quick statements user, the quick statements essentially behaves as a bot, but the difference here is that you have a human interfacing in between Wikidata. So the human is looking at the web interface and then modifying the CSV or whatever other kind of file it's using to write the data to Wikidata. So this is more of a cycle, but the human is the slow link inside that cycle. The VanderBot human team model includes writing to Wikidata, but also receiving data from the Wikidata Sparkle endpoint and writing some of that data to a local file. The script can also look up other data sources outside of Wikidata for additional information, use fuzzy string matching to try to decide whether external information is the same as what's already in Wikidata, and it only calls in humans when the rules that it's given are not clear enough about whether a particular item is the same or not. In order to understand how VanderBot does this, we need to take a little closer look at some details of the Wikidata infrastructure. So most people are used to editing Wikidata through the web interface. And when you do that, you're essentially editing Wikidata's relational database. You may also be familiar with using the query service. through its web interface. When you're doing that, you're actually accessing a graph database being run by the Blaze Graph application. So this is essentially a triple store that you are querying with your Sparkle query. So what VanderBot does, rather than using the web interfaces, it can write directly to the relational database by posting data to the Wikimedia API. And then it can also acquire data directly from the Wikidata query service using HTTP GET. One of the details that people aren't necessarily aware of is that these two kinds of databases are connected through an application called the Wikidata Query Service Updater. So it turns out there's not just one instance of the Sparkle endpoint. There's actually a number of them that are running simultaneously, and each of them are getting updated periodically. But sometimes there's a lag. Some of the endpoints have a lag of almost 0 minutes, but others could be lagged by as much as 30 minutes or even longer. So depending on which one of the query services you're connected to, there could be a delay in between data that's been written to Wikidata and when it then shows up in the Sparkle endpoint. And so VanderBot actually has to take this into consideration and not assume that the data that it's posted is immediately available. I want to take just a moment to talk about a few details of the Wikidata model. The reason why this is important within VanderBot is that the model itself determines the form of this complex Sparkle queries and also the JSON that is transferred to the API. The other thing is that key entities in the model are assigned identifiers, and these identifiers turn out to be very useful in tracking changes. They also place some constraints on how we store the data locally, and I'll go into some more detail about this later. So we're mostly familiar with creating items that have QIDs, and then we make statements about those items in the lower part of the web interface. What this looks like in terms of a graph of linked data, here's the subject item, and then the relationship or the statement is a connection between that and an object item. One of the problems that we have typically in linked data is how do we say things about particular statements? The way that Wikidata handles this is by creating a separate entity, which we could call a statement instance. And that entity actually has a randomly assigned identifier in the form of a UUID. If we know this UUID, we can refer very specifically to that statement. And we might want to do this because when we make a statement, it's really important to give more details about it. So for instance, if we say Brant Eichmann works at Vanderbilt, we might want to say what his starting time was. That's a qualifier. Or we might want to give references showing the source of the information and where we got it from. So the way this looks in the model, this statement instance is then connected to 0 or more reference instances, and those reference instances also have their own identifier. In this case, it's a hash, but if we know the hash identifier for a particular reference, we can look it up directly without having to connect it to any of the other things. The qualifiers are a little bit different. In many cases, the qualifiers are connected directly to the statement instance and they don't have their own identifier, although if they're more complicated things, sometimes they do. So there isn't necessarily any particular identifier for a qualifier. So this is relevant in the project because references and qualifiers are really critical to improving the quality of the data that's in Wikidata. But the connections, as you can see from those graphs, between the items, statements, and references can be kind of complicated. And so the question is, how can we document this complexity in a really simple way while still preserving the connections between them? And the answer in the case of VanderBot is through use of tables. The identifiers that we've seen for various kinds of data items in Wikidata can play some very important roles. So just to summarize, items, the item identifiers are QIDs that are sequentially assigned. Statement IDs are these randomly assigned UUIDs, and reference identifiers are constructed from hashes that are derived from the reference data itself. So if we know what these identifiers are, we can then use them through Sparkle queries to find out whether those statements still exist and whether they have changed or not. So we can check what is currently in Wikidata and compare it to what the state was when we wrote the data. This is useful not only to find out if someone has added new statements, but also as a possible mechanism for tracking vandalism to the data that we have put into Wikidata. The other way this is useful is that it allows us to keep a record of whether particular data that we've discovered already exists in Wikidata or whether it still needs to be written. And we can do this by having a column in our table where we, for each of these different kinds of identifiers, the QID, the statement UUIDs, or the reference hashes. And so if we have a piece of information and there's no identifier for it, then that's a signal that VanderBot needs to write that information. If there's an identifier, that's a signal that that information is already there. Once we write the data to the API, then the API will return JSON to us that includes the identifier of the newly written data, and we can then record that in the table and have a record of it without having to worry about this delay between when data is written to the API and when it's available through Sparkle. So I've talked a little bit about how we use these various identifiers to track the information in the CSV file. So let's talk a little bit more about the detail of how this file works. If you are a quick statement user, you know that that's also a way that you can take data in a CSV and put it into Wikidata. But the difference here is that the CSV format that VanderBot uses does not have any requirements about header names. So you can write, you can name them in any way that's clear to you. The column order is not important. You can arrange them any way you want. You can also have data in columns that are useful to a human reader, but that you want VanderBot to ignore. And then, as I mentioned, we have these identifier columns which keep track of the status of an item. If it's an item that was discovered in Wikidata, we know that it doesn't need to be written, but if it doesn't have an identifier, we know that this is data that we found elsewhere that needs to be written to the API. So given that this format is way more lax than what's in quick statements, then how does VanderBot know what the different columns mean? The system that I'm using is based on the W3C recommendation for generating RDF from tabular data on the web. It's basically an international standard for relating CSV tables to RDF. And so because the Wikidata graph model is essentially a linked data form of RDF, I can use a JSON LD schema as specified by this standard to map the table contents with the Wikidata graph model. And so doing so allows for two things. One, it allows the VanderBot's API writing script to know how to convert the CSV data into the wiki-based JSON that it needs to create to communicate with the API. But the other thing that's cool is that you can use this schema and apply it to the CSV data and have it emit exactly the same RDF directly from the table that you would get from the Wikidata query service. So what this means is that this is a stable and standardized way to unambiguously archive data in a very easy to read tabular form. So just to show you how this works, here's a CSV table, and here is the JSON mapping file according to the standard. So each of the section in the mapping file explains what's going on in a particular column in the table. If you have an application that knows how to do this mapping and to generate RDF, you can actually take the schema and the table and emit RDF turtle that is exactly the same as what you would get from the Wikidata query service. So the reason that this is an advantage is that CSV tables can easily be edited by a script, but also easily can be understandable by a human. And if you've used quick statements tables, you know that sometimes it's a bit obscure. The other thing is that this table then becomes a snapshot of the part of Wikidata that you're working with at any given amount of time. And so if you wanted to compare the status of Wikidata now with that snapshot, you can emit that RDF from the snapshot, put it into a triple store, and then query it with Sparkle in the same way that you query the Wikidata query service to find the current state of that information. And by comparing the results of those two queries, you can learn whether the data is the same or whether it has changed since the time when you wrote it to the API. So having given that information about the data model and identifiers and how that is stored in the CSV files, let's talk a little bit about what VanderBot actually does. VanderBot is actually not a single script. It's a series of 6 different scripts. The most relevant one to what I've been talking about is a general purpose API writing Python script. It ingests CSV of the form that I just talked about and writes its data to the Wikidata API. So in terms of the workflow, it's the last step.
The first thing that the script does is to read the schema to understand the columns in the table, and then it starts writing to the API. If the API has too high of a volume, then it will wait increasingly longer amounts of time, but keep retrying until eventually it retries at 5-minute intervals. The server lag dropped below 5 seconds, and it's now starting to write. Every time it writes a record, whether it's a new record or an existing one, the API sends back JSON that indicates all the data that is associated with that record, the pre-existing data, as well as the new data that we've posted to the API. So one of the things that the script does is to go through the data that comes back and to pull out the identifiers that are associated with the new items that were being written into Wikidata, because that's basically how it keeps track of which of the items have been written and which ones have not.
But the question is, how do you get the data into that spreadsheet? And that's what the first series of scripts do. They acquire and process the data that's stored in that CSV. There are 4 general steps. The first one is to acquire the data, and where the data comes from is going to depend on the data source. In the case of our project involving researchers, we scrape departmental websites. Each website's different, so this part of the script is very, very idiosyncratic. And then we perform a disambiguation step to try to determine whether those items that we're wanting to create already exist or not. And I'll talk more about this in just a moment. Once we've determined that certain items already exist, then we want to download the existing statements and all the identifiers associated with them and put them in the CSV so that the API writing part of the script knows that it should not duplicate that information. There's a lot more details. I've actually written a number of blog posts about this if you're interested in those details, but for now, this is the general scheme. So I mentioned that step 2 is really important. This is a disambiguation step. This is what makes the difference between a smart bot and a dumb bot. In the case of our researcher records, we make extensive use of ORCID IDs to help us with the matching. And then once we've sort of identified the people that we can, then we generate a lot of different possible name variants for the names that we've scraped from the websites, and then query Wikidata for all of those different variants. After that, then we have to screen through the possible matches, starting by eliminating possibilities that are very unreasonable. Then we use some fuzzy string matching. I'll talk about these 2 things next. And then finally, we can do some cross-checking against linked records, such as works that were created by the potential match. And after going through all these screening steps, if there is more than one possible match, then we present the human with information to help it make a choice, such as the description of the item, the occupation, and the employer. A lot of times there's only 0 or 1 Wikidata item that makes it all the way through the test. And in that case, VanderBot just makes a decision and the human doesn't have to be involved unless there's more than one possible choice. So just to kind of run through the kind of screenings that we do to eliminate unreasonable possibilities. First, we check, is it either a human or doesn't have any instance of a value? If it passes that screen, then we check the birth date to see if the person is too old to be working at Vanderbilt now. Or if they're dead, we also don't consider them to be currently working at Vanderbilt. And then there's a certain category of items, for example, Ming Dynasty person, that we know that could not apply, and we can screen those out as well.
So the first thing it's doing is downloading some information. There's a couple of researchers that it didn't find any matches for. It did, however, do a Sparkle query to try to find the orchid for this person here, and it was able to match them up with a record.
Once we've eliminated bad matches in that way, then we start looking at connected information. So for instance, if there are works or articles that are linked to that person and they're in PubMed, then we go to the PubMed API and see if that has any information that would allow us to either match with the orchid that we have or to discover that this person's orchid is incompatible with the one that we know that our researcher has. And then we try to do fuzzy string matching. If there is a departmental affiliation string in PubMed and it doesn't match, then we also know that's the wrong person. After doing those steps, if we don't have any success, we basically try again with Crossref to try to look for matching or exclusion. And if the potential match has an orchid, but the record doesn't have a full name, as we saw in the example of the dumb bot in the beginning, then we'll go to the ORCID API and see if we can find a better name from ORCID itself, and then try to see how well that matches with our researcher.
Let's check this person. Again, no other information, but if I have it check the articles, here's some articles, but the institution was in People's Republic of China, so that's not a good match.
I've mentioned fuzzy string matching a number of times. This is a really powerful aid for making decisions about whether the names that we've scraped from the websites are the same as the labels that we find in Wikidata. Fuzzy string matching basically ignores minor punctuation differences like periods. If there's diacritics, those don't cause any problems. And they're actually, the Fuzzy Wuzzy library has several different matching algorithms that you can use depending on the kind of string. If it has multiple words, then you can decide whether you care about the word order or if you care about only matching subsets of the words. So by experimenting around with this, I was able to come up with cutoffs for an upper cutoff. So if the match is better than a certain score, then VanderBot automatically says it's a good match. And if it's below a certain cutoff score, it automatically rejects it. And then there's a range in between where essentially VanderBot is unsure, and in those cases, that's when it has to ask a human for help. And so determining these upper and lower cutoffs is something that you have to do empirically by running a test set and then determining how many times you get false positives or negatives depending on different cutoffs. And you adjust the cutoffs until you get as close to 0 false negatives and positives as possible. The interesting thing is that these cutoffs can vary depending on the how large the pool of potential matches is. So for example, if you're matching against any possible item in Wikidata, then those cutoffs have to be more stringent, whereas if you're matching against a list of known Vanderbilt people, then they can be the cutoffs can be more lax. So what I've described here is kind of an oversimplification. There's actually a number of more steps, but you can break them down into the 4 general categories, which is acquiring the data in the source, from the source, doing the disambiguation step, downloading existing data from Wikidata, and then using the API writing part of the script to actually write the data up to Wikidata. If you're interested in the details, there's an 18-minute video that basically runs a department through each step of the script, and you can see exactly how that works. So just to end, this is what I was able to accomplish with VanderBot. VanderBot has made over 8,000 item edits. And as I said earlier, this is more than 8,000 statements because each item writing incidents could involve more than one statement. Usually there's 3 or 4 statements being made in each edit. So nearly all of the over 4,600 Vanderbilt scholar and researchers now have items that were either created by VanderBot or they were linked to pre-existing items. And once this was done, we, in a separate project involving clinical trials that I'm involved in, we were able to create 933 links between researchers and clinical trials using a new property that we requested called Principal Investigator. Now that we have linked the researchers to their departments, we automatically now have created over 20,000 works that are now linked to Vanderbilt. These are not works that we put in ourselves. They were already linked to the researchers, but by connecting the researchers to Vanderbilt, we now know that Vanderbilt departments were responsible indirectly through the creation of the over 20,000 works. So this is real leveraging of linked data. So that's kind of the results in a nutshell. There is a lot more information, some Sparkle queries where you can play around with the data, and also, as I mentioned, the video, which you can see at vanderbit.lt/VanderBot.
Steve, thank you for that presentation. Is there anything you'd like to add?
No, I probably could talk for another hour, but I tried to summarize it there, but I'm happy for any questions that people have.
I see there's been a variety of questions, and I see you've been answering them on the Google document Q&A page. I've put a link into that Q&A page onto the group chat in Zoom here. If anyone has not seen or can't access the Q&A document or can't find the specific section for this presentation and all of the answers that Steve has been providing throughout the presentation, please write back in the chat here and I'll send it to you directly again. But there's been a fair bit of conversation there, and Steve has been very active in making sure the answers are forthcoming.
Actually, the last question that was asked, I might elaborate on that a little bit.
Certainly.
The question was asked, could you just do this in OpenRefine? And another member of our team actually was using OpenRefine to write to Wikidata for the similar sorts of purposes. But I wanted to have something that was basically completely modifiable. And although the process that I described here requires human intervention, what I intend to do in the future is to take pieces of VanderBot and repurpose them. So for example, I mentioned the idea of doing maintenance on data we already put in. So for example, going through and periodically and checking, are all of the statements that we made actually still there? And then, create a list of things that that got changed so that they could be reviewed for vandalism and things like that. So I think my intention was that I would repurpose various bits of VanderBot, and in many cases, they would be more automated. The disambiguation part, it's very difficult to completely automate with, with a high degree of accuracy. But for some of the other maintenance sorts of things, I would want it to be able to operate a lot more autonomously. And I realize that you can script OpenRefine, but I think still ultimately requires a lot more button clicks than having a script. I also should mention that, like, I'm intending to use this for a bunch of other things, like disambiguating all of the natural history museums. We're about ready to disambiguate a bunch of journal titles.
So although this is like very specifically related to people, I'm hoping to adapt the script, at least the earlier parts of the script, for disambiguating and uploading other types of things besides just researchers.
Thank you, Steve, for that clarification. I've put a link in the chat here as well to OpenRefine itself, for those who are not familiar with that software, which is a standalone and more general software. It's not Wikidata specific, but it certainly is very powerful and very useful for Wikidata purposes. If anyone has any further questions, please go over to the Google Doc, which has been linked a couple of times in the chat. And Steve, I assume you'll be around for a while yet, able to answer any further questions should people have them.